This is an example of how to solve an entire circuit for the voltage through each resistor and the current through each resistor. So the first step is you should always simplify furthest from the battery. So you work from the outside, the outermost portion of the circuit, to the inside. Again, you work furthest from the battery, inward. So clearly these resistors R1 and R2 are parallel. Next, you have to know that parallel resistors have equal voltage. So we write the voltage through resistor 1 equals voltage through resistor 2 equals V12. Now that last statement, where I equate to a third voltage using the subscripts 1 and 2, this is a great technique. So it seems really random, but you'll start to see why it's important. So next we do the equation for resistors in parallel. So the total resistance of resistors 1 and 2 combined would be 1 over R1 plus 1 over R2. So this would be, let's see, this equals 1 over 440 plus 1 over 520. So 1 over R12 would be 0.00420. Now remember, that's 1 over the desired quantity. So the actual R12 is when we do 1 over to both sides. So we do 1 over 0.00420, and we get about 238 ohms. And that's the same as raising our decimal to the -1 power. Also keep in mind an alternative to that equation is doing, so this equation here, for resistors in parallel, an equivalent formula, an algebraically equivalent formula, would be total resistance equals product over sum. And you could prove that through algebra yourself by multiplying both sides of the equation by the least common denominator. But I'll save that for another video. I'm just going to do it the way that I started. So next we can do step 2. So if you notice the second scenario, once you simplify this circuit and express R1 and R2 as one equivalent resistor, R12, notice that one resistor would be in series with R3. So R12 is in series with R3. The current through resistor R12 equals the current through resistor 3. And then do one more statement, which includes all subscripts. So resistors in series have equal current. So now we could do the total resistance R23 would be R12 is in series with R3. This is 238 plus 690. So R123 is 928 ohms. Excellent, almost done. So now that's step one. We simplified the entire circuit to find the total resistance. So when we combine all those resistors, R1 and R2 and R3, this is the total resistance of the entire circuit. So now the next step, so step one is find the total resistance of the entire circuit. In this case, there's only 3 resistors. The next step is Ohm's law using R123. We can find I123. So using the resistance in the entire circuit, find the voltage. No, find the current in the entire circuit. So the current should be V total voltage over total R. Now the total voltage through the circuit is always the given voltage, the battery. So V123 is 14. Again, the goal is to use R123, which is what we just found, to find I123. And this gives 0.0151 amps. That's the current through the entire circuit. Now, this step, I love this process. So again, this is use R123 to find I123. And the question that arises, well, this seems contradicting, right? Why would I want to find the total current in the circuit if my goal is to find each individual current? I don't want all of them combined. I want each individual current value. Well, look back at step 2. Once you have I123, it's actually equal to I12 and I3. So for the first time, we actually did find an individual current value, which happens to be I3. So now, after you find the total current, you could start finding individuals. So let's try the next. I noticed how we had to work backwards to notice that. So now what you do is you keep working backwards. So you work back to the previous step, which would be step 2. And again, what did it state? It stated in step 2, we saw that, let me see, I12 equals I3 equals I123. And initially that didn't help us at all, but then we realized, oh, I123 happens to be (0.0151). So this number here is 0.0151. So are all of these. Good, so let's find everything we possibly can. We could find, yeah, using our I's, we can find our V's. So now I'm going to use Ohm's law in its most common form, V equals IR. So now I can find I12, or V12, using I12. So this is 0.0151, the previously found current, times R12. Well, that was 238. This gives 3.59 volts. Good. So we want to also find the voltage through each resistor. This is a voltage through a combination of resistors, both 1 and 2. Okay, we're getting there. Here we can find V3 because the next thing is I3 times R3. Again, I3 is still 0.0151 times resistor 3, which is 690. This gives 10.4 volts. Now we used all the information we could from step 2. Next, we go back to step 1. Step 1 stated that voltage 1 equals voltage 2 equals V12. Okay, so not only am I going back to step 1, but I'm going back to our previous step. According to our previous step, V12 was 3.59. So we're in luck. This was the voltage through multiple resistors, but it's also the voltage through individual resistors, both 1 and 2. With these individual voltages, we can find individual currents. So I will use Ohm's law rearranged for I. So I1 should be V1 over R1, 3.59 volts over R1, which is 440. 3.59 divided by 440 gives 0.00816. Current is measured in amps. Next, since we have a V2, I2 should be V2 over R2. This gives 3.59 divided by 520 equals 0.00690 amps. Excellent. So now we found all currents. We calculated an I1, we found an I2, we found an I3, I believe. Let me make sure. Yes, we found an I3, a V1, a V2, a V3. Now let's do an alternative procedure. So if you want to know another way to solve this problem, you could also use Kirchhoff's laws. So it's just a different way of solving the same circuit. So what we can do is we can look at all currents flowing through the circuit. So from the battery, there's a current I1. Once it reaches this point here, this is a junction. It's a fork in the road. The current splits into an I2 and an I3. It's like water flowing through a pipe. If it encounters different paths, it's going to take each path. Next, I'm going to circle around each portion of the circuit. So this is going to be our loop 1. And this other half of the circuit is going to be our loop 2. I always use my left bottom corner to be the starting point of each loop. So as I move around my loop, so first I'm moving up. So I'm moving up, but my current I2 will be flowing down. Even before that, let me just make sure. I'll call that little point A. That's the point where the current splits. And notice how, actually, let me just do a little rough diagram on this page so we see what happens. It's not as neat, but it'll do. So this was R3, this was R2, this was R1, and this was the battery. Okay. And we said this special point here, we called it point A. And this is the point where the current splits. So all the original current was from the battery. Here's our current approaching point A, and then it splits into an I2 and an I3. So at point A, we have I1 going into point A. We have I2 exiting point A, so it's minus. And then we have I3 exiting point A. And you always set it equal to 0. Next, you always want to solve for I3. So if you rearrange this equation for I3, you should get I3 equals I1 minus I2. So that's how you get your first equation. I always suggest you rewrite your third current in terms of the others because you don't want 3 variables. You could take that third variable and express it in terms of the first 2. So this is like saying z equals x minus y. So anyways, the next thing you want to do is, we said this was, wait, let me double check. We said this is going to be our loop 1, and this is going to be our loop 2. So here I'm going to traverse the circuit clockwise. And I choose to start from my bottom left point. So if I go around the circuit on my own, notice how my I2 is going to be flowing down. But I am going to be going up. So here's me, I'm going up against the current. When you flow against the current, it's actually positive. So equation 1 is a voltage gain. It's going to be positive R1, which is 440, times I2. Notice that's an I times an R, so this is my positive voltage. And then the next thing I do is I'm flowing this way along the circuit now. I'm flowing down, which is the same direction as my current I3. My current I3 is also flowing down, so that's a voltage drop. So now I'm going to have minus R2, which is 520, times I3, but I3 is I1 minus I2, and this is always set equal to 0. Because now I traversed that entire first loop. And I'm back to my starting point. Now, if I go along this starting point, here in red, the first thing I encounter as I go up is that I'm flowing against I3. So that's going to give me equation 2 will be a positive R2, which is 520, times I3, which is I1 minus I2. Next, we are moving. So first we're moving up. Now we're moving to the right. But the current I1 is moving to the left. So we're going to have a positive 690 for R3 times I1. Next, we're moving down. So we're moving down towards the battery. The longer side is the positive terminal. The shorter end is the negative terminal of the battery. If you go from positive to negative, it's a negative. So this should be negative 14 volts equals to 0. Now, before I write my equation 2, I actually like to simplify each equation one at a time. So usually I simplify my equation 1 first. Let me actually just simplify that. So to simplify my equation 1, I still have my 440 I2. So this is still my equation 1. 440 I2 minus, now I'm going to distribute my 520 to get 520 I1. And then a positive 520 I2. And this is equal to 0. Then I combine like terms. So I get 960 I2 minus 520 I1 equals to 0. Then I box this equation. That's my equation 1, but simplified. Now my equation 2, actually let me write the original. It was 520 times the expression for I3 plus 690 I1 minus 14. I always distribute. I still have my 690 I1, and I always move my constant to the right-hand side. Combine like terms. This gives 1210 I1 minus 520 I2 equals 14. So that's what I usually do. I usually would write my equation 1, then simplify it, then write my equation 2, then simplify it. Next, I compare both equations. I had to solve a system of 2 equations, 2 unknowns. In this case, I usually try to use the elimination method, but we actually can't. So I'm going to do the substitution method. So I'm going to rearrange equation 1. I write that as 1 prime to represent that I rearranged equation 1. So we will add 520i to both sides. And then divide both sides by 960. So at this point, it's pure algebra. It's a math problem. We're just solving a system of equations. So we get I2 is, let's see, 520 over 960. That gives us 0.542 I1. Good. And then the next step is to always plug the expression for I2 into the next equation. This becomes, okay, so we get equation 2 was 1210 I1 minus 520 times I2. But I2 is this expression. So that's 0.542 I1. And recall this was equal to 14. Perfect. So now this becomes 1210 I1, distribute the negative 520. So we get negative, or not distribute, but just multiply. Negative 281.8 I1. Combine like terms. We get 928.2 I1 equals to 14. Divide both sides by 928.2, and we get I1 is 0.0151 amps. Good. So this is the current through resistor 1. Oh, well, actually, no. Be careful because we are going to solve for the currents, but I1, just because of the labeling of the diagram, I1 actually passes through R3. So this value we just calculated, this I1 is the current through resistor 3. So we have to be careful. But we can go back and check the work. The current through resistor 3 was 0.0151. Perfect. So it is consistent. Okay, let's just finish this off real fast. Almost done now. That was the long part. Now we could plug the numerical value for I1 into either equation. For me, I just plugged it into equation 1 because I feel like that was the simplest. Equation 1 was, let's see, 960 times I2 minus 520 times I1. But now we know that I1 is 0.0151. So then we get 960 I2 minus 7.85 is equal to 0. When you add the constant to the other side and then divide both sides by 960, you get I2 is 0.00818. Good. Finally, the last current, we have to go back to the equation at the point A. It was I3 equals I1 minus I2. So now we could find that third current by plugging in our I1, which was 0.0151. Then we minus I2, which is 0.00818. So finally, we obtain I3 equals 0.00692 amps. Oh, messy. Anyway, so that's both methods to calculate the currents and voltage through each resistor.